Okay. So let's do this. So I've got, oh Jesus, I'm not going to show you. So up here, so we did GCF is always step 0. You always see if there's a GCF. If every term has something in common, get it out. If you have 4 more terms, grouping. That's what we did when we underlined and did a couple of GCFs, yes? That's the x minus 4 problem we did earlier. 3 terms, that's what we started doing with the x squared plus 5x plus 4, right? We did an example where a is 1. So we want to do an example where a is not 1. It gets a little bit trickier. And then, of course, there's difference of squares and difference or sum of cubes. So let me do this. Let me show you an example where a is not 1. We'll do an example of cubes. And then we'll talk about functions for a bit. Okay. So what if I had this? What's interesting to me is it looks like I've noticed students doing this kind of thing. Does anyone do that? Yeah. You do? Okay. All right. So I'm going to show you the way I was shown how to do this kind of problem. But if you do something like this, that's fine. I will tell you exactly the way that you are not allowed to do it unless you can explain why it works. Is that intriguing? The problem with this is I can't just get factors of 6 that add to be 5 because that 4 is going to mess things up. Yes? Really want this to make sense. So here is how this sort of works. I want to show you an example. So to investigate this, I can do what I did here. I did an example where I multiplied it together and I figured out, 10 came from 2 times 5, 7 came from 2 plus 5. The basic thing about mathematics is trying to find a pattern, yes? And if I do a problem and I see a pattern in the way things are put together, I can then use that pattern to pull them back apart. And that's what the factoring really is. So, if I do an example of 2 binomials where the first term won't be 1, so something like this. I'm just making stuff up out of nowhere. There we go. Can you guys take a moment and multiply that out for me? Do the multiplication of that. Multiply that out for me. If you're doing it in your head, that's neat. If you don't have a pencil, let me know. So I can berate you and then give you a pencil. Do you have a pencil? You do? Okay.
I'm trying to do it in my head.
Okay, gotcha. I like this, the challenge.
Instead of doing it in your head, it's me.
Yeah. All right. So let me catch up to you guys. Let's see. Okay. So 2x times 3x, 6x squared. 2x times negative 5, negative 10x. 3 times 3x, 9x, and then 3 times negative 5. Now, I can combine the middle terms, correct? Do it, it's fine, but notice this. What is negative 10 times 9? What's negative 10 times 9? Negative 9. What is 6 times negative 15? Huh?
I said 90, but
It's negative 9. It is. Real quick, guys. Look at me. 6 times 15, yes? That kind of sucks, yes? Take a factor of 2 from 6, what do you have left? Take 6, take a factor of 2 out. What is it? 3. Take the factor of 2, put it to 15, what's that now? 30. Yes? 3 times 30 is 90. So anytime you have a number that ends in 5 and you multiply by an even number, steal a factor of 2, make it 30. Now it's easy as shit to multiply them together. Does that make sense? You with me? No? Or don't, because I know you have calculators, but still, we're humans. We should know how these numbers work, correct? Aren't you a little curious as to how people can do stuff in their head so quickly? I'm not going to try to make you into human calculators, because I'm not even a freaking human calculator. I just know some tricks, right? Okay. That is trippy, yes? Negative 10 times 9 is negative 90. 6 times negative 15 is negative 90. And then if I put these together, okay, so here's the trick. I have to take the first number into account because it gets mixed into the middle terms. Do you all agree that 2 and 3 is where 6 came from, yes? When I multiply those together? Doesn't 3x get multiplied and 2x come on, they mess up the middle term? Do you see what I mean? Doesn't that first number mess the middle term up? Okay, so here's the method to factor something like this. In fact, we'll do this one, and then we'll do the one where we have no idea what the actual answer is, yes? Here I know what the answer is, it's right there. So, if I see a number that's not 1 here, in front of a trinomial, free term dude, you take the first times the last, and we just figured out, what is 6 times negative 15? Negative 90. Now I find factors of negative 90 that add to be the middle term, negative 1. And you already know what that is. Negative 10 and 9. Let me stop for a minute. So I still find factors of a number that add to be another number, but since the first number is not 1, I have to take it into account. So I multiply 6 by 15, that's the Nooch step. Then I find factors of that number that add to be the middle number. That's the same as what we did before, right? With the 4 and the 5 we did before, yes? I just have to take the 6 into account to begin with. Then these tell me how to split the middle term up so then I can group and get the answer. So let's try this one. What's the first step on this? Is the first number a 1? Is there a GCF? No, damn it. So if you see a 4 there, you're like, let me take a 4 out. No, shit. So what do I have to do with the 4 then? What's the very first step? 4 times 6 is 24. That's insane. And I'm realizing I need a minus in there, Jeff. Do I? No. Yes, I do. Okay. Let me do one little thing. Change one little thing. Make this a minus. Okay. So now we make this negative 24, yes? Now I need 2 numbers that add to be negative, that multiply to negative 24, add to be 5. Are there 2 numbers that multiply to negative 24 and add to be 5? Negative 3 and 8. See, that's the exact same step we did earlier when it was x squared plus 5x plus 4. It just was easier earlier because the first number was a 1. It didn't mess anything up. Does this feel familiar to anybody? Has anybody ever done this before? Yes?
No.
No.
I got a question.
What you got?
So, my brain wants to take one of the x's out.
Oh, sure. The only problem with that is it doesn't come out of everything. You see what I mean? Sort of like if I said factor 19. Can you factor 19? No. But if you said, okay, that's 18 plus 1, and then I can take a 9 out of 18. What? No, the plus 1 has to be, that you can't just take. So I can't take a piece out of a subtraction addition problem and call it factoring. Because if I factor something, what's the only operation at the end? Multiplication. Does that make sense? All right. So I don't blame your brain, because your brain's like, there's a bunch of x's. I should be able to take an x out. But it doesn't come out of everything, so it doesn't work. Because then the poor little minus 6 would just be left out in the cold, right? Poor little dude. So, if the first number is not a 1, you take it into account. Negative 8 and 3 add to be negative 24. Break the middle term up. 8 and negative 3. Because that multiplies to be negative 24, and that adds to be 5. So how can I rewrite 5 8 minus 3. I use these two numbers to break up the middle term. Now why is that good? Because now I have 4 terms, and I can use what? Grouping. So that's what this called. I was taught this, and I was told this is called the surefire method, because if it is factorable, surefire, this will work. I did grow up in Georgia, but I moved away when I was 5. I didn't move away, my parents didn't, they took me. I didn't drive somewhere. So I wasn't taught this in Georgia, but surefire sounds like a Georgia thing. Surefire is going to work. So if I do grouping of this, what happens? What comes out of these two? 4x, and what's left? Good, there's the 4's gone, one of the x's is gone, so there's 1 x left. 8 divided by 4 is 2, and the x is gone. Yes? What comes out of these two? -3, good, because you know you want your result to be positive to match with this guy. And sure enough, this divided by -3 is x. -6 divided by -3 is 2. What tells me I'm on the right track? The two parts are the same, so what can I do? If I have two things that are the same, I can take them out. So if I take an x plus 2 out, what's left? And you can literally do this. 4x minus 3, yes. Now some of you guys, again, you might use, I think one of you guys said you use this method. If you don't know what it is, great. Don't do it that way. Some of you guys might use trial and error. And some of you guys are sitting there going, I do not remember doing this. So I am a blank slate. So then do this. There is, I almost hesitate to say this, but there is a method where you take these and you divide by 4 and you do some magic and the answer comes out. Now I know why that works, because I'm Mr. Math Boy. But if you know that method and you want to use it, some teachers call it bottoms up. It's true. If you want to use it, you have to explain to me why it works. If you don't know it exists, good. Let me stop for a minute. How you guys doing? Y'all look very excited. Okay. Factoring, I can't tell you. Maria can tell me if I'm crazy or not. Factoring is one of the most necessary skills if you want to get any further in mathematics. It's insane. And of course, if you want to get any further in any STEM field, you need more math, which means you need to understand factoring. So I can't stress enough how important it is to understand how to factor things. Okay. So let's do this. That's right. I still have to talk about cubes. I can't remember if I told you guys, has anybody ever seen the movie Pulp Fiction?
Yes.
All right, if you haven't, you're okay. It's not a prerequisite for the course. If you've seen Pulp Fiction and I say this, you'll know what I mean. The scene where something horrible happens in the backseat of a car. Yes. And then they have to call somebody to clean stuff up. Yes, okay. So this method of factoring cubes somehow references that movie. So remind me of this, guys. Remind me of this. Let's do a nice one just to get into it. This is not a cube yet, obviously. Can you guys remind me how to factor this? How do I break this one up? X for x squared, right? What else happens? Yeah, plus, minus? 4. Now, why does that make sense? Because I started with 2 of everything. So I just broke everything up into parts and put them in. There were 2 x's, so xx. There were 2 4's, that makes 16, so 4 and 4. So the trap you could fall into, if I put this, is you might think, oh, I just put 3 things here, and I put x, 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 and I put 2, 2, 2, because then I'm going to break everything into 3 parts. I mean, so far the logics, but this don't work, because no matter how you make these signs, right, you won't have everything cancel that you need to cancel. So that is not how cubes works. Okay, and cubes is probably the least liked, the most hated factoring form, because it's the one you have to memorize the most. The other ones you can kind of sink your teeth into it. You can break 16 up and all kind of stuff. This one you have to kind of memorize how things go. So, help me out, guys. X cubed. That's x times x times x, right? What's 8? 2 times 2 times 2. Okay. You put my little cube down here so it doesn't look too weird. Okay. So the way you do a cubes is you put a little dude and a big dude. You with me? Oh, I heard something that's interesting. My favorite sounds is like, oh. X cubed, there's 3 x's, yes? And look at the little dude. Look at him. He's a cute little dude, right? I'm not going to try to shove too much. He's just a little dude. So I'm going to put 1x in there, and I'm going to put 1, 2 in there. Is that cool? So it feels like squares so far, yes? Because what did we put here? We put 1x and 1, 4, yes? Okay. This sign will always be the same as what it is here. What must go here then, considering I put 1x there? The other 2 x's. What must go at the end here, considering I put 1, 2 here? The other 2's, 2 times 2 is 4. So do I get my minus 8? As long as what sign is on the 4? Plus. In fact, this one is always positive. All right, let me stop for a minute. Now listen, my hope for this class, and I can see some of you guys glazing over a little bit, I desperately want to get to the why does this work? Not just memorize this shit, because the more you do that, the less connection you have, the harder it is to memorize. I want you to know why things work the way they do. Can you guys all see, if I start to FOIL this out, I do get x cubed. And I do get minus 8. Do I get anything I don't want? Don't I also get this? What's this? Yeah, I also get plus 4x. Yes, I get plus 4x. And I get minus 2x squared. Yes? Do I want those? This can't be the answer, can it? Because it has these extra pieces. Yes? Okay. So 1x, 2 x's. 1, 2, 2 2's. So now I just need to figure out what can I put there. And this is the connection to Pulp Fiction. I got to call the guy to come clean. I think it's called the wolf in the movie. Who saw it? It doesn't matter. You don't have to. So I need help. I need to clean up the stuff I don't want. I need something in the middle that will clean this stuff up. So what would I multiply 2 by to make negative 4x? Because I want to cancel this, yes? What would I multiply negative 2? What would I multiply negative 2 by to make negative 4x? So these would cancel. 2x. What would I multiply x by to make positive 2x squared? 2x, holy shit. So, 1 of each, 2 of each, product in the middle. That middle dude is the weird one. 1x, the other 2x's. 1, 2, the other 2 2's. That makes sense. Because I got 3 of everything, 1 of each, 2 of each makes 3. This one is the one that gets students stripped up. He's the cleanup guy. He's the guy that kills the stuff you don't want. Gets rid of it. Yes? Get not life lessons, kids. Don't do that. So this one, this is the product of whatever the hell is in the little guy. Whatever is here. X and 2, so this is 2 times x. If it was m and 7, this would be 7m. You guys see that? And the sign is the opposite sign to this. And what word did I just write? Soap. Yeah, so what's funny is, soap is something that was used to remember this, and it goes perfectly with my Pulp Fiction, because they had to clean the back end, what they have to use a lot of. Frickin' soap. All right. By the way, Pulp Fiction is a little intense. So if you haven't seen it, maybe read up about it before you do, if you want to try it. Okay. So here, let's do one more of these. Just because this looks like the sketch of a football play. It's a little hard to follow. So let me do one that's a little more interesting. 8y cubed plus 27. Sure. So first step is really identify it as a cube. So how many terms does it have? How many terms? 2. So it can either be squares or cubes. It's obviously not squares. You have to make sure it's cubes. Is every element, can you break it up into 3 parts? Yes. So if it was 8y cubed plus 25, can't do shit with it. It's not squares, and it's not cubes, so you can't do anything. You with me? Okay. Can you break each term up like we did earlier? What's 8y cubed? Break it up. What does it take 3 of to make 8y cubed? 2y. So it would be 2y times 2y times 2y. And of course 27 is 3 times 3 times 3. See how far you can make it. Try to piece this together. Go ahead and try to break this up. Oh, I'm going to say this because otherwise I'm going to forget. Does everybody see how Maria is right there? She's actually right there, I know, but she's sitting there when she's not saying. Anytime during lecture or whatever, if you want to kind of gravitate to Maria and ask a clarifying question, like you don't want to interrupt me, you can do that. Does that make sense? When we stop like this, both Maria and I are available for questions, yes? You with me? But if I'm like doing stuff, like I don't want to interrupt this guy, let me go ask Maria real quick what he meant by this. You guys with me? Okay, so it's another bonus to having Maria in here with us. One with 2 terms and one with 3 terms. That's why I say little do, big do. Yeah. Yeah. Almost. So, okay. This is good. 2y, but here's the mistake here. When you multiply these together, do you get equal? So it's not just 2 squared. No. Yeah, so you square 2y, which is 4y squared. The last term was beautiful. The middle term has got to be whatever's here multiplied. What is this times this? Yeah, and then the sign is the opposite of what it was in the old. Okay. So there's one more mistake. The little dude, the sign is the same. And this sign is the opposite of the plus. So the little dude sign's got a plus, and this guy got a plus. Cool.
I know I didn't show that.
No, you're fine. No, there's not much work to show, to be honest. Yeah. It's good. Oh. Yeah, okay. All right, now listen. If you really think about it, the steps that go into this are not difficult. They're just kind of unwieldy to remember, right? That's why I'm not the biggest fan of little sayings like FOIL. I think I already told you about how I feel about FOIL. But I do like this. 1 of each, 2 of each, this is always the same sign, this one's the opposite, and then product in the middle. 1 of each, 2 of each, product in the middle. That's the closest to a song you'll get me, blah, blah. Okay. I've seen people make songs out of the quadratic formula. Negative e plus, like whatever, stop. How are we doing? I really want the reasoning to make sense, but then just the more the reasoning makes sense, the easier it is to remember how to construct this. So what would have changed if this would have been a minus?
The first one.
Yeah, this would have been a minus. This would have been a plus. So This is always the same as it ever was, and this will be the opposite of what that is. Why does that make sense? Because what's this guy's job? To cancel shit. So he's got to be the opposite sign so he can actually cancel stuff. Okay, maybe. So the more you understand why things work the way they do, the less it's memorization and the more it's just doing what's right. I don't have to memorize, don't put my hand on the stove when it's on. And I'm like, shit, I forgot to remember that. No, it just makes sense not to. Yes? Okay. I'm not saying math is like putting your hand on the stove, but it's okay. All right. I don't know. Let's see. All right, listen. I'm going to allow you guys to pick 3 of these to try. Are there 3 of these you'd like to try? Give me which one of these would you like to try? I'll let you pick one, and then I'll pick 2 more. Is there any one of these you want to try? So on the other side of that paper you have, yes? Which one would you like to try? Number 1? Kick ass. All right, so do number 1, and then I'll pick 2 more for you. Number 4. And number 3, that's fine. So 1, 3, and 4. Try those out. Let me or Maria know if you need help. Oh shit. Are you poor little dude? Okay. What's up? So if you need to, you can flip the paper over and remind yourself of the steps. Understand? So this one. Yeah, sorry. 1, 3, and 4. You can do whatever ones you like. They're all going to be good practice. Yeah. The only thing here is, what's 8 times 2? Yeah, so it should be not 2a, but a squared, so take the 2 out front of it, right? See, that's good. So you're right, your brain was saying 2a. Yeah. Like, wait a minute.
Big 2,
Yeah.
It seemed like too easy. I was like, sure.
Try filling it out.
Okay.
Alright guys, I'm gonna catch up to you. 2 terms. It can only be squares or cubes. This one's obviously squares, not just because it's a square, but there's no GCF. You can break everything in half. So how do you fill in these parentheses? Yeah, x plus 9, that's fine. Yeah, so it doesn't matter which one's first, because multiplication is commutative. X, 9, 9, plus minus or minus plus. Kick ass. So let me show you an example. Here's a good, all right, let me just make this up. Show you one. 49, w to the 10th, z to the 40th, y to the 28th, minus, how you guys feel so far? 16, a to the 8th, b to the 24th. Okay. Now, I don't know if anybody out there is like, all right, math person, stop it. How many terms did I just write?
A lot.
Nope. How many terms did I just write?
2.
Each term is packed, but there's only 2 terms. You guys see that? What are terms separated by? Plus and minus. There's only one subtraction happening, right? There are 2 terms. The first term is big as shit. Yes, there's a lot of stuff in the first term. The other term is big, just not as big. Are you guys with me? So I wrote a lot of stuff, but I only wrote 2 terms. So what could it be? It could either be, so in terms of factoring,
GCF.
you had GCF. Is there a GCF?
No.
No. So it can only be cubes or squares. Can you cut everything in thirds, or can you cut everything in half, multiplicatively? Half. All right, you guys understand all the steps I just went through? I don't blame you. If I gave you this problem, it would be a little mean, because there's just so much going on, and you're like, holy shit. But how many terms? 2. No GCF. Oh, so it can only be cubes or squares. I can cut everything in half. I need you to understand what I'm about to say. It automatically has to be easy. If it's squares, what do? You take everything, cut them in half, plus minus. Yes? I don't care how much shit there is. This is the point I'm trying to make. This is sort of like that weird little scene with Yoda. He's like, size matters not. So there's a lot of shit in there. But the process doesn't care. It is squares, difference of squares, easy. Can you cut everything in half for me? Give us a lot of room. 49. When I say cut it in half, you all know I mean multiplicative, yes? 7, 7. W10. W5, W5. Z40. Z20, Z20. Y28. Y14, Y14. If you multiply these together, don't you get 49? Add the powers, add the powers, add the powers, you get all this stuff, yes? Was that hard? No. Did it look like it was supposed to be hard? Hell yeah. I need you to see the difference. So many times students give up when it wasn't a lot of work. It just had a lot of parts. Minus plus or plus minus. And of course this is not too bad. What's this? It's going to be 4, 4. A4, A4. B12, B12. And it sounds like finance. Do you start to see what I'm saying? I'm not going to necessarily, every test I'm going to have a bonus section. I could probably beef one up even more than this and give it to you as a bonus, and some of you guys will realize, oh, this is not that big of a deal. Yes? Maybe? Okay. So this is something I started saying to a lot of my classes. Math doesn't care what's in the problem. The process is what matters. So I see a squares, I see a difference of squares, 2 terms. It doesn't matter how much stuff is in it. The process doesn't change. Cut everybody in half, plus minus. Okay. So what about this one? I want to give you not too evil of one based on what we just did. Didn't we basically do this one? A cubed is, let's break it up. A. 8 is 2, 2, 2. I know it's a cube, so I put little dude, big dude. What goes in the little tiny dude? 1A plus 1, 2. Then A times A. And at the end I put 2 times 2. And then what's the middle term? Minus, because the opposite sign, 2A. So the middle term, very little thought. Opposite sign, whatever's in the little dude, put them together. Yes? Maybe? Is that okay? All right. Cubes, again, people don't like cubes because if it's been a while since you did one, you suddenly have to do one, you're like, oh crap, what goes where? It just, you have to memorize kind of like how things flow. But 1 of each, 2 of each product in the middle. Okay. What about number 4? What do you have to be careful about? What mistake do you think students might make? What mistake do you think somebody might key in on? What piece of this? They'll see the 3. They'll see the cube, and they'll see the 8, and like, oh, it's a cubes, but why is it not a cubes? 50 and x. So what do you always try first? And this is why I haven't really been doing this like correctly, because I should first rule out GCF. Yes? So what comes out of both? 2x. What do you get when you take that out?
4x squared minus 25.
Yeah, 8 divided by 2 is 4. 3x's take 1 away, it's squared. 50 divided by 2 is 25. I had 1x and I took it out. Am I done? No. What can I do with this? Yes. 4x squared is 2x times 2x. 25 is 5 times 5. Minus plus. Or plus minus. Alright, how you guys feel? Is it, you remember some of this?
Yeah.
Okay. Now listen, I'm not thinking that after that quick little thing that you're gonna necessarily know exactly how to factor everything in the universe, but with this sheet, with you, and you do the homework, section 1.5, I think it is the first section of homework, you have the sheet sit next to you, and then just reference it as you do the problems, right? Go to the tutoring center. So if you hit something you don't understand, you can have somebody explain it to you. It's crazy. And again, I can't stress to you enough, I don't mean to like make you tense about this, but factoring is big. Factoring shows up whenever it is, whenever it needs to, it's gonna be there. So we have to have a good grasp on factoring. Okay. And by the way, is anybody curious why the shit we factor things? Yes?
Yeah.
Beautiful.
Yeah, I kind of like, what's the point?
I love it.
Yeah.
Kick ass. So, let me see. Well, let's do this. What if I wanted to reduce this? Yeah, I have to factor the top. How do you factor the top? And then what can cancel? These can cancel. The only things that cancel are the things that are the same, yes? When you divide two things that are the same, it becomes one. So then I know this is this. If that's not good enough, real quick, how do you solve that? This is stupid, right? How do you solve that? Nothing major, right? Subtract 4. Ooh, math boy. Way to go. Now, how do I solve this? Can you get x by itself? Do you see what I mean? Can you get all your x terms put together into one term? You can. What is x squared minus 6x? Make that one term for me go. Are those like terms? So let's try this again. The way to solve an equation normally is you get all your x's together on one side. Together, fully together, yes? And all your numbers on the other side. Can I do that shit here? No, I have two things that have x's in them that are not like terms. You with me? All right, so watch. If I just do this, what would I do? Add 8, divide by -6, right? Beautiful, because I'm getting all my x shit. I can't get my x shit together now. So what the hell do I do? Here's what you do. Can you guys help me? How do you factor this? Did I make this factorable? Now it is. Good job, John. How do I factor that now? X and x. Now two numbers that multiply to be 8, add to be -6. Good. -4, -2. Those multiply to be 8, add to be -6. Now, look at me. If I told you I multiplied two numbers together and got 0, what must be true? I multiplied two numbers together and I got 0. What must be true? If I had two numbers and I multiplied them and I got 0. One of them has to be 0. You with me? If I multiply two numbers together and I get 4, does either one of them have to be 4? Does either one of them have to be 2? Does either one of them have to be anything? No. The only number that I can equal when I have a product and know what to do next is if it's 0. Do you guys see two numbers I'm multiplying? X minus 4 and x minus 2. If I knew what x was, aren't those two numbers? All right, so what did we just say? What did you just tell me? If I got two numbers multiplying equals 0, what must be true about at least one of the numbers? Either this one is 0 or this one is 0. So either x is add 4, x is 4, or x is 2. Now, real quick, in a grander scheme of things, you could still say, well, how does that help me buy lettuce? I actually had a student ask me, we did some math, and they said, how does that help me buy lettuce? I'm like, literally. I'm like, not everything helps you buy, what are you talking about? So I don't know if they're trying to be cute or something. Solving equations is the most basic thing in the universe if you want to do any frickin' STEM at all, any of it. You have to solve equations, yes? So when I start amping up the power, the degree of the thing I'm trying to solve, I need other ways to solve it. And so when I have a power other than 1 on one of my variables, I get it equal to 0 and try to factor it. If I can't factor it, does anyone know what I would do? Some other thing you have to memorize. Quadratic form, right? Okay, I'd rather do this, yeah? Okay. If I can factor it, I do. All right. So, let me ask you this. How many of you guys have gotten this? Anybody else? Anybody? Okay. I do have more of these. Right now, I'm trying to think about. Yeah. Okay. So let me give you. I don't know if that was enough. Scopings. Oh. Do you have a book? Yeah. Oh, cool. Take that. There. So this was put together by Sharon Giles and Steve Davis, 2 of my colleagues. But really, we all kind of got together and gave them stuff to kind of throw into this book. So before we really get into this, you can see up there that functions. What do you guys remember about functions? Anybody know anything about functions? Like, what does function notation look like? Pretty much see it right there, yeah. But do you guys remember, like, well, it says here, f of x and g of x? Okay, so here's the big thing. When you start to do stuff like graphing and so forth, you might have equations like this. Yes, we're not going to suddenly start talking about slope and y-intercept, not yet. That comes later. Do you guys remember, if you were going to graph this, do you guys remember when you would make an xy table? So you would start picking values of x and plugging them in, yes? What if you had multiple equations? And even some of them maybe have different stuff happening, yes? How is it easy to keep track of which one's which if they each are like y? If I just said, what's y when x is 3, what would be a really good question you could ask me? Yeah, which y? What the hell are you talking about? So, one immediate thing we can do is we can give each one of these its own name, right? Okay. And even, like, if this is an equation for the amount of helium in a balloon after so much time, then I would call it h of x. Or I'd even call it h of t would be even better. Because I can then match the letter with the meaning. You guys with me? Okay, if I had a garden growing tomatoes, I can make the t function for the number of tomatoes over time. Okay. The other thing this does for us, let me see what you guys think about this. If I ask you, given these 3 functions, if I said to you, what is f of 1? Now there's no question about which function I want you to use, correct? So all you have to do then is what? What is that asking you to do?
Plug one in.
Yeah. The funny thing is asking you to do exactly what just happened. What did I do? I replaced x with 1. So it's asking me to replace x with 1 in the f function. And of course, what do you get? That's crazy. So can I see the point that this function goes through? What was my input? In this expression right here, can you tell me what the input was? What did I input? 1, and what was the output? 3. So that's the other advantage function notation has. I can see on one line what I put in and what I got out. Can we stop for a minute? The most important advantage is what I started with, is I can identify multiple functions at once, just give them each their own little name, f, g, h. Okay. Not surprisingly, math people being creative as we are, we're like, functions, let's use the letter f. So that's why they start with f and go to g, go to h. Okay. Yes?
So is the entire thing the function, or just like the part that says f of x, or like?
So f
Or
of
like
x
the
is
one
the
in the
name of the function, and x plus 2 is what that function does. So I got the f function, I got the g function, I got the h function. And what does f do when I plug an x into it? It adds 2 to it. Does it make sense? What does the g function do when I put something into it? What's the g function do to a number? Triples it, takes 1 away from it. So one of the most boring ways to look at a function is like a machine. You put something into it, it does shit to it, and then out pops the result. Yes? Okay. In my head, I always think about Willy Wonka. I don't know if you guys ever saw it. And the machine goes, and then the little gobstopper comes out at the end. Yes? Okay. Again, you don't have to have seen Pulp Fiction and I'm thinking about, Gene Wilder, Willy Wonka, the really good movie, not the. I love Johnny Depp, but dear God, what the hell happened? Okay. All right, so let's look at this. We have this function notation, so I try to tell you why we kind of came up with the idea. Domain and range, do those sound familiar?
Yes.
Okay. So, let me see. Let's just go from here. If I had the function x plus 2, is there any number I can't add 2 to? Is there any number that I cannot add 2 to it? Do you understand what I'm asking? Like 7, can you add 2 to it? Yeah, it makes 9. Negative 148, can you add 2 to it? All right, is there a number I cannot add 2 to? No, I can add 2 to any number, correct? The domain is the collection of all inputs that work. Domain is all the inputs that work. So for example, if my function is x plus 2, what did we just say? Are there any inputs that would not work? No, I could plug anything in. I can add 2 to anything. So what's the domain? All real numbers. I like it. We'll talk about integral notation later. So domain is a collection of all the inputs that work. The range is a collection of all the outputs that I get. Okay, I like it. So in this example, I don't really like this picture, but it's okay. It looks like little weird moldy potatoes. They don't really tell me what my inputs are, which is one reason why I don't like the way we've done this. But it looks like X is one input. And you see how it has output of Y? I'm not sure. They really should have done a better job of this. Okay. So let me do a little better job. So let's say I have 1, 2, 3, 4, 5. Yes? Domain, range. What's the output for an input of 1? 4. You guys see it? That's how you read that kind of a diagram. So inputs are in the domain, outputs are in the range. So what's the output for an input of 3? 5. Is there any input that has the same output as another? 1 and 2. They both have an output of 4. You guys with me? Okay, I like it. Okay. This by itself is what we call a relation. You're going to get very tired of me referencing movies. Has anybody ever seen Highlander? Highlander? It's okay. In that movie, there's this thing about there can only be one. So the domain, so a function is a relation where for each x, there can only be one output. For each input, there's only one output. I like it. So for example, if I square a number, is it possible to get more than one output? No. What do you get when you score 7? 49. What do you get when you score -5? 25. I mean, I can't get more than one output, correct? That is a function then. For every input, there's only one output. I like it. So, for example, let's break this down a little bit. Can somebody tell me, I'm going to ask a different question than what's being asked here. This might be a little weird. Can somebody tell me what the domain is? If this is the function here, if this is the collection of inputs and outputs, what's the domain? Remind me, what is the domain in general? All the inputs, and the inputs are the x's. So what would the domain be here? 2, 4, 7, 8. Kick ass. So it's literally a collection of all the inputs. Now, I have a finite number here, so it's easy to kind of like enumerate. So I would write it like a set. 2, 4, 7, 8. And of course, what's the range then? 3. There it is. Okay. Do it again, sorry. 3. 1. -1. 2. Sweet. Now, can you tell if this is a function? What does it take for something to be a function? For every input, there is only one output. So look at part A. Is there any input that has more than one output? 2 goes to 3. Does it go to anything else? No. And so forth. Can you guys very quickly see that is a function? It matches the definition. What about part B? Just tell me if that's a function. Tell me exactly why not. Yeah, like 5 has more than one output. I want you to be really careful. Let me see. -2 has an output in -1, correct? 4 has an output in -1, correct? That's not a problem. If I ask you what size shoe is on your left foot, you're going to tell me one answer, right? If I ask you what size, could you have the same shoe size as he does? Could you, physically? Yes, you could. So 2 different inputs can have the same output, and it's still a real life thing. It's still a function. One way I look at a function is it could represent something in real life. If I throw a ball 3 seconds later, if I say, where is it 3 seconds later, and you tell me 5 feet up and 20 feet up, I'm like, what happened to that ball? What do you mean? How can it be in 2 places at once? So for a function to have only one output for every input, I think of it being something that could be real life, right? You can't be in 2 places at once. And if you can, tell me how. That would help. So this guy is not a function, not because of this, that's fine, but because of this. This is saying at 5 seconds, he was 3 feet up and 2 feet under the ground. Right? And then you're like, is that guy okay? What happened to him? I don't want to know. Right? Okay. So for every input, there can be only one output. But some inputs can have the same output. It's fine. Okay. So, this problem here. What does it take to be a function again? Every input can only have one output, correct? Okay. Can you imagine, is there a number you can square, take 4 away, that you get more than one output? This one's kind of funny because I want to point something out. If I plug a number in for x, don't I get y? Yes? So if I can solve an equation for y, it's a function. If I get 1y for every x that's a function. So what's wrong with part B? Can anyone identify why part B might have a problem? The y is squared. If I try to solve for y, this is a little bit tricky. If I try to solve for y, what would happen? Let's see. What would I do next to get y by itself? And if I take a square root, does anyone remember what I have to put there? Real quick, what do you square to get 9? Or 2 squared is 4. What do you square to get 9? 3 or negative 3. It's easy to forget. You're fine.
I thought you said 4 or 3
Oh, I'm sorry. I was a little worried when you said 2. But it'll be all right. So I want you to realize if I take a square root, I have to put a plus or minus. So that is not a function, because for any input, don't I get 2, a positive and a negative output? Now also, and again, this is a little bit beyond where we currently are, but just in case anybody's seen this before, does anyone have any clue what this is a function of? I mean, not a function, but what this would look like if I graphed it? No. If the x wasn't squared, you'd be right.
A circle.
A circle. Okay. So later in the semester it'll be, oh no, look at that. So here's the great thing about the definition of function. I can make it into a visual, like Maria has. Can you guys see on Maria's picture? Do you see she's drawn like a vertical line? And she said, That point right there, this point right there, what do they have in common? They have the same input. So is there an input that has more than one output? Does this input have more than one output? Yes. You guys with me? I can make the definition of a function into a visual test. Sam, have never heard of the vertical line test? Okay. So that is the visual representation of the definition of function. Every input can have only one output, so if I draw a vertical line and it goes more than twice through the function, through the graph, it can't be a function. Because that would mean an input has more than one output. And I think they finally get to that. Maybe not. Poor little guys. So we'll do it right here. I think it's on my handout. The vertical line test. If you can draw a vertical line through a graph, and it goes through more than once. Not a function. That's the volt, the vertical line test. Okay. Thank you, Maria. Some of you guys were shaking your head in recognition. You heard this before. Okay. So, real quick, let me see. This is kind of a review here based on what we did earlier. Can you guys do number 3 and 4 for me? Or at least number 3, and maybe try number 4. 4 might push you a little bit. So do exactly the same thing on these. Yeah. That's all function notation is substitution. Okay. Blush. So if you keep in mind that the basics of function notation just wants you to substitute values in, it doesn't matter what's in there. This might freak you out at first, but it's exactly the same problem as that. So can somebody tell me what's the first step to figure this out? Yeah, so you literally, if you just write underneath the question, what did you just do? You replaced x with -4, so you replace x with -4. And how do you do this, of course? You get 20 plus 3, 23. So if I were to graph that, which we're going to do, of course, later this semester, if I were to graph that, what point would that go through? -4, comma, 23. An input in -4 has an output of 23. Kick ass. Now let me ask you a side question. So if f of x is -5x plus 3, what is f of Maria? Function notation doesn't care what's in it. It always has the same exact process. It's very single-minded. Whatever you put in it, you put in it. Yeah, -5 Maria. -5 Marias plus 3. So a little Maria black hole, strength 5. So now look at example 4. A little bit weird. I'm not trying to shove a whole person into the function. What am I going to replace x with?
X plus 3.
Yes! So if f of x is x squared minus 6, f of x plus 3 is x plus 3 squared minus 6. I really... And this is directly related to things you're going to have to do in calculus. Yes? So like I told you guys, this is pre-calculus, but really trimmed down to exactly the skills you need for calculus. The more sense that makes, and then am I done? Can I do any more? Can I simplify that? Yes, I can. Can't you square that? All right. You might not want to, but you can. So calculus, you're going to be doing the same stuff. You're going to have functions that you have to do stuff with, and you're going to have to be able to shove entire expressions inside of other functions. Yes? So it's like a turducken of stuff, if you ever heard of that. So what can I do here? How do I FOIL this out? Let me write it twice for myself so I don't forget anybody. Let me continue to write horribly. Check. So then I get, how do I do this? X squared plus 3x plus 3x plus 9. Thank you. So we get x squared plus 6x plus 3. Bam! So literally it's just, if I said f of w, you would say w squared minus 6, right? It's so single-minded. It's just replace this with this. That's all it is. Okay. Let me ask you this. What's the domain of this? So, when I say what's the domain, math is a foreign language, yes? You're at the stage, potentially, with some of the stuff I say, of just learning new vocabulary. So you have to translate in your head. So when I say what's the domain of this, you translate that to what inputs am I allowed to use? Because domain is a collection of all the inputs, yes? You can even look at it as, are there any numbers I'm not allowed to put in for x? Is there any number you can't square? And I don't mean by hand, I mean just theoretically, right? So I'm, like, I can't square 25,948,000. I understand. But you could square, you can put it in your calculator, yes? Okay. So this domain would be all real numbers. All reals. What about if I had this function? I just want to show you an example of a function that's got a problem. That function's got a problem somewhere, yeah? It's, if you try to put a number into it, a certain number, it will freak out. Does anyone see what that number might be?
2.
Yeah, why? What's the problem with 2?
0.
Yeah. What happens when you divide by 0? Bad things. In fact, it's so bad we call it undefined. We're like, we don't even want to talk about it. Okay. When you get to calculus, I can't wait for something, because when I say undefined and all this kind of stuff, you start to investigate it further in calculus, and you start to kind of like understand what that really leads to. We will talk about it a little bit. In fact, some of you guys might know, you guys know what an asymptote is?
When you get so close to 0, but you can't like write it down.
That's one example, yeah. So like this one, if I graph it, it would have a wall at 2. Why does that make sense? What input am I not allowed to use? You told me it's 2, right? So I'm going to put a wall at 2 because I'm not allowed to use 2. And if I get really, really close to 2, what does the bottom, like 2.1, 2.0, isn't the bottom getting tiny? Can you guys see that? And if I divide by tiny, what's my answer get? If I divide by smaller, smaller, my answer gets bigger, bigger. So that's going to lead to this kind of behavior. Okay, that's way ahead of us, but I just want to throw that out there in case anybody's ever seen that. That's the connection between something weird happens at 2. The domain does not include 2. Well, what the shit does that actually mean graphically, for example, right? So the way I would say the domain here is, I could either say x does not equal 2. Let me throw this at you guys. Does this look familiar to anybody? Yeah. We just really throw that out of nowhere at you guys. So this means all the numbers from -infinity up to 2, or from 2 to infinity. So what's the only number this leaves out? 2. So I look at this as skip 2. I look at this as piece of saying skip 2. Yeah.
Would it have to be the bracket?
Oh, the bracket means you include. So real quick, since you brought that up, do you guys remember on a number line you would put an open circle when? If you don't want to include it, and you would put a closed circle when you include it. See, a parenthesis looks like part of an open circle. So a parenthesis means don't include. A bracket looks like part of the letter I for include. So a bracket is include. Yes? And I always liked it when I taught this. Remember you use shade? And then you would put a parenthesis here and a thing there. And somebody always told me, how do you know which side to put the bracket? I taught using Dragon Ball. Anybody know Dragon Ball? Kamehameha. So the parentheses go like this, and then the shading comes out from it. Yes? If you don't know Dragon Ball, you're fine. Again, I'm very sorry for all the extraneous references. You don't have to watch Dragon Ball. If you do, I would highly recommend you watch Dragon Ball Abridged, where they replace all the dialogue. It's hilarious. Somebody knows what I'm talking about? Vegeta. I'm very sorry. Coming back. Okay. Oh, good. Here it is. Beautiful. Perfect time. Interval notation. So a small value up to the maximum value. Let me ask you this. I'm going to just give you guys this to look at. Look at 7. For the moment, well, let's see. Let's see what you guys think. I want you to notice something about the first one. The kinky one, right? The one that's like this. Yes? It's a wrong word, but it's got somebody like kinked it. Yes? Okay, thank you. You're like, how do you tell anything about it? So, do you guys see the arrows? That means it keeps going down forever, yes? So, somebody help me out. Which axis would be related to the domain? Because what's domain again? The collection of all inputs. And what letter, what variable do the inputs normally associate with? X. So when I want to know the domain of a function I'm given the graph of, look at the x-axis. If I had a little dude walking on the x-axis, and remember, this goes forever, yes? Is there anywhere he won't see an output? See, if he's here, he sees an output here, correct? If he's here, he sees an output there, yes? Is there anywhere he won't see an output? So what's the domain? All real numbers. And how do I write that in interval notation? Where do you start? Smallest. Negative infinity. It's way back here to infinity. Kick ass. If you put a bracket here, what I would want from you is I would want you to bring infinity to me. Because if you put a bracket, you include infinity, and I personally think that's when the briefcase in Pulp Fiction is infinity. But again, sorry, second Pulp Fiction reference. You can't put a bracket on infinity because you can't get there. What is infinity, by the way? Does anybody know? What is infinity? I like that. That's a beautiful answer. You're like, it's infinity, man. So it's not a number, correct? It's a process. One way to define infinity is start with 1, add 1, continue. That's infinity. Is 1 closer to infinity or is 7 closer to infinity? They're both the same distance. That's trippy. I'll stop talking about infinity. So don't put a bracket on infinity. Don't put an infinity on a number line. Because then you're like, how did you get past infinity? How did you get to infinity? Holy shit. Okay. What about the range? We haven't talked much about the range because the range is a little bit funkier unless you have a graph. What's the range again? Collection of all the outputs. Is there a lowest output or a highest output on this graph? Highest one. If there's no lowest one, that means there's no floor, yes? So what is the lowest output I could get? Negative infinity, sweet. Comma, 3, beautiful. You guys see that? So if I'm walking on the y-axis, I see it way down at negative infinity, and then I stop seeing it at 3. Yes, good lord, that looked weird. If I try to go past 3, do I still see the graph? Do I see the graph looking left and right? No. So if you have a little dude walking on the x-axis, that's your domain. Little dude walking on the y-axis, that's your range. So how would I write that down? What symbol? Start at negative infinity, so I would put a parenthesis, because you can't get to infinity. Up to 3, and do I include 3? Is there an open circle at 3? So I would include 3. So what's the biggest difference between this problem and that problem in terms of what I just said? Is there an open circle on my graph on this problem? Yes. So what's the domain of that one? Have a little dude walk on the x-axis. Now, are there points at the ends? There's not arrows, so it starts and stops, yes? So have him walk. Where's the first time he sees it looking up and down? Negative 3, he sees it. So that's where the domain starts. Do I include it? Yes. So I put the thing that looks like part of the letter I. And where does he lose sight of it? Right at 2, yes? Now what I'll get people to do is they'll put like negative 3, 1. But that's wrong because isn't 1.99999999999? Does that work? So instead I say 2, but I just don't include it. Yeah. Okay. So you guys take a second to do the range. What's the range of that thing? But do you see how it's a closed circle? So there should be a bracket. And what's the highest output you see? Good. And it's not an open circle, so you put yes. Beautiful. All right, let's see. This is a you know it or you don't moment here. So if I'm walking along on the y-axis, the first time I see him is negative 5. And what kind of symbol do I put on that? Bracket. And then as I walk along, the last time I see him is 4. Is there an open circle there? So then I put a bracket. Okay, sweet. Now this doesn't matter. Is there an output of 0 here? No. But is there an output of 0 here? Yeah, so I didn't have to skip anything from a range because I do get all those outputs from -5 up to 4. Okay. And I kind of already did this kind of problem with you. Okay. So, real quick, can you guys just tell me what value messes this up? Which means the domain is what? Everything except 6. I like it. Now, look at this guy. Okay. Can you, real quick, what kind of number would I get if I put a number in for x? What kind of answer would I get? What kind of number would it be? Whole number would it be? If you put a 3 in. Yeah, not irrational. It's rational because it's a ratio. Yeah, it's a fraction. You guys agree? What can't happen in a fraction? What cannot happen in a fraction? What are you not allowed to have show up in a fraction? 0 where? Okay, so if I said, tell me in English what can't happen here, you would say bottom can't be 0. Yes? And then you would write, so in English, bottom can't be 0. Now, real quick, I'm sorry. This is not English, this is Jeffish, which is kind of related to English. What is the bottom? X minus 6. How do you write can't be 0 in Mathish? Can't be 0. Add 6, x can't be 6. Okay. So what I'm trying to tell you is, look at this. Can you tell me in English what must happen or what can't happen? What kind of number can a square root handle? What kind of number can you put into a square root? Or let me say it this way. What kind of number can you not put into a square root and stay real? No, what's the square root of 0? 0. So 0 is fine. Negative. Right? So what must be true about the inside? Well, it has to be positive or 0, yes? Now, guys, for a number to be positive, how must it be related to 0? It's a great question. Greater, yes? So the inside must be at least 0. That's in English. Inside, at least 0. Then in Mathish, inside, at least 0. So if I give you a function and I say, what's the domain? You say in English what must happen or what can't happen, and then you write what you just said in Mathish and solve. Now we haven't talked about solving inequalities yet, but it's the same as solving equations, except for one thing. This is the last thing I'll tell you tonight because we're just about done. And you guys have done a great job of dealing with me today. Do you guys remember, and Maria's like, I've drawn on the board a couple times. Thanks, Jeff. Do you guys remember the one thing that's different when you're solving inequalities? So, for example, let's start off easy. How do you solve this inequality? Subtract 1. So it feels like, okay, it's the same as equations. That's very true. There's only one difference. There's only one place where something different happens. Yes. So can you guys, side note, just out of nowhere, which one of those is bigger? Holy shit. Now, if I divide both sides by -1, what does this become? 2. What does this become? Which one's bigger? What did the sign do? Okay, so when you multiply and divide an inequality by a negative number, the sign's got to flip. Why? Because it does. So when I multiply and divide by a negative number, whatever side of 0 the things are on switches, so whatever was bigger is now smaller. Does that make sense? Okay, I like it. Sweet, okay. Yeah, I'm going to stick to my word. So listen, I was talking to Maria earlier, and I want to say this directly to you guys. And I said this really quickly last night. I don't know if you guys picked up on this, but you could have gone into 180 and taken like 080, 180, but you are smart. You said, wait, shit, I want some freaking refresher. So the great thing is I do have a bunch of concepts that I want to get through in this class. The truth is, you didn't have to take this class. So something I realized was, anything you get from this class will help you more than if you would have just went to calculus without it. So I don't mind if we kind of stay with an idea for a little bit. So again, if I'm going too fast over something, dear God, slow me down, because we can stay with it for a little bit. You with me? I'd much rather you understand fewer concepts from this class than I get through all of them and you didn't really understand any of them. Yes? Okay. All right. That's enough. And by the way, I want to point out, Maria did put some more examples of like, so if it comes back on itself, it's not a function. As long as it doesn't do that, it is a function. So that's fantastic. And she's got one with an asymptote that kicks a lot of ass. Okay. So that's good. And let's see, you need a authorization, right? And everybody else, if anybody else needs to see me, come see me. Otherwise, I'll see you tomorrow. And then we have a bunch of time off until Monday for this class. Yeah. Okay. Thank you. You don't have to buy the book.